Alright, today we're going to basically conclude with going through Chapter 6, which talks about different type of parallel processing architectures, as well a little bit about the cloud, because everyone loves the cloud. So we're going to breeze over this chapter and only highlight a couple things that are important, and this is due to basically the way this course turned out, not necessarily from the lovely situation we're in, but also because of the interesting position that this course is in, being a transition between the standard way of teaching and then the new way that's going to be x86 and excuse me, and with a little more math oriented with discrete math. So we're going to go through different types of parallel processing, and then I'm going to highlight a couple of them that will be important for your homework, and then we'll conclude. So what's the point here? Well, we've talked a little bit about how we can increase performance of a single processor by going single cycle, multi-cycle, and then into pipelining. There are other techniques in order to increase single cycle performance, but there does appear to be an end to how fast we can make a single processor go. So the point of parallel processing is to try and take advantage of using multiple cores or multiple processors in one box. Nowadays, pretty much every processor has multiple cores. That used to not be the case, but nowadays it is. And so we want to figure out, how can we do this? How can we take advantage of this? And there's different ways to go about it. Well, we want to make it scalable so that each time we add a core or a processor, it increases by that much amount. We want to make sure the cores are available, and then of course power efficiency is also a big concern, because as you have more and more cores, of course, you're going to consume more and more power. Generally, we talk about task level or process level parallelism, and so the idea this is for a high throughput for independent jobs, but there are other ways to go about it. And let's see. Oh yeah, multi-core processors, which what we're talking about is a chip with multiple processing cores on it. So hardware-wise, serial, the Pentium 4 was definitely a serial chip. I love how they list a quad-core. Well, yeah, the quad-core Xeon is definitely parallel, and the Xeons are still being made nowadays. Software, sequential matrix multiplication is pretty sequential, because in order to compute the next one, you really need to know what's happening previously, as we showed in a previous course. Concurrent, though, and operating systems concurrent, because you might have completely separate processors running, or processes that don't interface with each other running. But sequential and concurrent software can run on both serial and parallel. The challenge is to make effective use of the parallel hardware when it's possible. Alright, we have talked a little bit about parallelism, although not at this level. In 2, we talked about parallelism and instruction synchronization, so this is with pipelining, where we're taking instruction parallelism. We're executing basically 5 different instructions at the same time. We're just choosing which part of the instruction to execute. Computer arithmetic, so subword parallelism. But another good example, I think, for this one is with matrix multiplication, where you had the pipelined approach, so you could again have multiple multiplications, I said it right, going through the ALU. And then there's advanced instruction level parallelism. A little bit about out-of-order parallelism, and then parallelism memory hierarchies. We did not go into that, so don't worry about that. Parallel programming is the problem. We need to get significant performance, otherwise we might as well just use a single core processor, because it's way easier to deal with a single core. Those of you continuing on to operating systems, you will thoroughly understand this. Those of you that are stopping here, namely from cybersecurity, one point I haven't been able to fully make, but hopefully you'll realize at some point, is that writing code to take advantage of parallel or multiple cores is highly, not dangerous, but highly error prone, because there's a ton of difficulties of partitioning everything out correctly, coordinating it to make sure everyone's on the same page, everyone has the right piece of data, and then there's communications overheads as well with communicating with all the different cores. From a security standpoint, each of these has a chance of introducing some type of bug in the software. So parallel code in general is way more complicated than sequential. We did not talk about Amdahl's law due to the nature of this course, but the big takeaway here is that Amdahl's law is basically you keep attacking the problem that is the bottleneck until it's no longer the bottleneck, then you find what the new bottleneck is and attack that. I.e., how do you increase performance? We'll find out what's slowing everything down, make that the fastest thing so that it's no longer the bottleneck, then repeat, aka go to the next bottleneck, and so forth and so on. And let's see. So also, that was with Amdahl's law, which talks a bit about parallel or sequential. Let's go into a scaling example, which can be very useful. So let's say we have 10 scalars in a 10 by 10 matrix sum. So speed up from 10 to 100 processors. Single processor, well, there's 10 scalars, aka 10 things, and there's 100 each, and it has 100 items, okay, because we're adding 10 to the 100 times the what's to add. Okay, great. So we're going to add 10 values to a certain part of the matrix. So this is the time. By the way, this is just t-add, how long it takes to do an add. Well, 10 processors, you still have the same number, but the 10 by 10 matrix is the part that you can parallelize. These scalars have to be done sequentially. So divided by 10 is 20, which means that the speed up, originally it was 110, now it's 20, and so the speed up is 5.5. Well, if it's scaled completely, it would have been a speed up of 10, but the problem is only the 100 is the part that's parallelizable, not the 10. So that's what limited to 5.5 speed up. Well, let's throw 100 processors at it. Well, let's just say that those 100 operations in the 10 by 10 matrix got done perfectly in parallel. That'd be 11. 110 by 11 is a speed up of 10, not 100. The point this is trying to make is that when you parallelize something, there is a limit to how much parallelization you can actually utilize. Nearly all problems have some part of sequential code, at least at startup, but even the algorithm itself, a lot of parts of it are sequential, which means that throwing more and more processors at some point is not going to do anything. But let me show you an example. What if the parallel part was 100 by 100, aka 10,000? Well, let's run through the numbers again. Well, with 10 processors, it's this 5 by 10. Speed up is 9.9, and that's 99% the potential of 10. So that's a really good speed up, by the way. That's pretty solid. If I ever got 9.9, I'd be pretty happy. Well, let's throw 100 at it. Crunch the numbers again. It's 90, speed up 91. That's actually still pretty good. I'd be really happy with that as well. Usually anytime I'm above 80% with the parallel, I'm pretty happy. But notice that it is starting to go down. It went from 99% to 91%. As I add more processors, this number is going to start decreasing. So again, the point here is that not everything's parallelizable, but also if you can increase the space that's parallelizable, then of course you can utilize more processor. This should be intuitive, but here are the numbers to back it up. So strong versus weak. Strong, the problem size is fixed, as in the example we've always said how the size of the problem. Weak scaling, the problem size proportional number of processors. Alright, we're not going to worry about this too much, but notice that sometimes when you add more processors, you have to do more overhead as well. So at 10 processors, it's a 10 by 10 matrix, but due to the overhead of having 100, it's a 32 by 32 matrix as well. 32 by 32 matrix instead. We're going to move on from here, but just recognize there are situations where when you add more processors, the problem space necessarily increases because of communication overhead. Okay, I cannot recall if I've showed y'all this before, so I'll do it again. This is called Floyd's taxonomy. It is a way to look at the different types of processing out there. And so there's two main categories. You have instruction streams and data streams. Instruction streams are single, aka one thread, or multiple, where you have multiple threads. So aka is there only one program / thread working, or are there multiple threads working? So those are the two options here with your instruction stream. On the other side, you have your data stream, which is talking about how much data can you process at a time. Are you only processing one element at a time? And that's what we've been doing in our single cycle and pipeline processor. You have you're doing one add, and you're storing that one add into one register. Multiple data streams would be if you have multiple pieces of data and you need to store them into multiple registers. Again, I can't remember if we went over this, but a good example would be if you had pixels, which are in red, blue, green, alpha, we'll just say. So they have 4 values and you wish to add them, multiply them, or whatnot. Well, those 4 values do stay inside of a 32-bit register. So you can have instruction to do 4 8-bit adds, because if you divide 32 by 4, you have 8, which means that you have 4 8-bit fields. So you can do 4 8-bit additions, multiplications in one instruction at a time, and so that's what SIMD is. Alright, so let me go through an example to make more sense. So sysd, this is what we've been talking about so far, where you have one thread executing and you're operating or storing into one register. So you have an add and it stores that value into one register. So Intel Pentium 4 and any type of single-threaded application. SIMD, you still have one thread of execution, but you might have a special instruction, SSE instruction, that can do those 4 8-bit adds in one instruction. So it's one instruction telling you to do 4 adds, and there are instructions to do more adds, 8 adds, 16 adds, 32 adds, and all the different multiplications, floating point, etc., etc. But it's one instruction, but they're doing multiple types of data arithmetic. MISD would be if there's multiple threads executing on single data. There's no examples of this because it kind of doesn't make that much sense. But MIMD does make sense, because if you had about 4 sysd threads and you put them on 4 different cores inside a program, then you have MIMD, where you have multiple instruction streams and they're executing on multiple pieces of data. So a parallel program on a MIMD computer is generally what we're talking about for this, although we will talk a little bit about SIMD. We are not going through this MIPS example because we did not do MIPS. Alright, vector processors. I'm going to quickly go over this. The idea is just what I talked about back here, where we have a single instruction that's going to execute multiple adds. The question is, how do we have a machine that can perform these multiple additions? Well, usually it's called a vector machine, and I'm going to skip right over to the picture. Let's just look down here in order to save on the brevity of time. The idea is that over on this side you would have, if you're trying to do a bunch of adds, let's say you're trying to add, looks like 9 elements in an array, you'd have to line them up and send them through your ALU one at a time. So it execute 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9. What a vector machine is, well, let's go have 4 of these adds, and let's try and send multiple of these through at the same time. So I don't know why it's pictured 4. Yeah, so 4, 5, 6, 7, there we go. And so we can do 4. So it could do these 4, and then it can do those 4 the next cycle, and then it would have to do these last 2 at the end. So the point of this being able to do 4 at a time, it can do basically a speed up of 4 of these instructions. Now, notice that you have to have 4 additions in a row in order to take advantage of this vector machine. And that's the big if when working with vector machines, although a lot of times there are certain situations where you're just adding a bunch of numbers into an array or doing multiply or whatnot, aka matrix multiplication, and that's where this vector machine comes in. The reason I talk about vector machines a lot, and we're going to skip all that for now because we need to go to GPU, because the GPU is actually a huge vector machine. Let's go take a picture of that. It is basically, you have a bridge from your host PC that communicates to the GPU, and we're going to, again, for the brevity of time, skip a lot of this, but you have multiple computing units, TPC, and inside of those you have different SP, which are the streaming processors, and each of these streaming processors are the ones that can do the add, the multiply, so forth and so on. And if you look at this, it's basically a hierarchy of a bunch of streaming units inside of a streaming module inside of a TPC, which is a core, and then it has basically a compute work distribution. So the idea is that the CPU sends the work, it distributes it out to all of these different processing units, and then there's some network and storing it back into RAM, and then at some point the CPU could get it back, or well, most of the time a graphics card is doing some type of graphical computation, so of course it needs to just be displayed to the interface. How this looks, well, you might have your CPU, something called a north bridge that talks to memory, and a north bridge talks to the south bridge, which is where your VGA controller and whatnot are, and so it can communicate. There are other ways where the north bridge is part of the CPU. That's very common nowadays, and then it can communicate to the GPU through chipset. The old Intel one was to have a north bridge communicating south bridge. South bridge is what talks to all the different peripherals, LAN, UARTs, aka serial, and USB and whatnot, but the north bridge here would also talk to the GPU. There's different architectures, but the point is that the CPU and the GPU are separate, and they communicate through some type of medium, usually a north bridge or a chip. And the north bridge is also a special processor built to facilitate the communication between the two. All right, I went over that briefly because it is important from architecture for you all to know what's going on, but we're going to talk about a different subject next, which will be more pertinent to your homework, and that will be multi-threading. So let me take a break here.